Okay, we're going to go ahead and get started. Thank you guys all for coming. Welcome to the May 2025 Journal Meeting of the Mount Diablo Astronomical Society. Thank you all for coming. Any new members or first members here at the meeting tonight, welcome. Thank you for coming. Welcome, thank you. If you need to use the restroom, you can just go through those double doors. You'll see them on the left. We're going to have a break after our What's Up speaker. Marianne has set up snacks in the back. Free artichokes and free kumquats. First come, first serve, but don't be a pig. Okay, be a pig. It's abundant. All right. So tonight we have a very exciting What's Up presentation by MDAS member John Corlett. Cannot wait to hear about his dark matter. And then we'll have a break. And then this evening we have a talk by Dr. Michael Busch from SETI. He's going to be joining us from somewhere not in California via Zoom later on. Okay, so community outreach is hopping this month. You know, the KINs can use your help. The Contra Costa Library Exploration Stations have several events this month. They're expecting 400 to 500 participants at each event. So these are daytime events. If you have a solar scope or solar filters or any kind of daytime activities, they could really use your help. The first one is Friday, June 6th at Doherty Station Library, and then the next 3 Wednesdays at the Walnut Creek and the Brentwood, and then the Hercules Libraries. All get there at 10 a.m. to set up. Presentations are from 11 to 1. So if you want to help out, please let them know right away. Our public observing night is Saturday, June 7th. Hope to see you guys up on the mountain. And next society observing Saturday, June 28th. And just a reminder, anybody interested in astrophotography, we do have the special interest group that meets on Zoom, and their meetings are, next meeting is Monday, June 16th. If you're not a member and need to get the Zoom link, you can do it through the groups.io MDS imaging group. You can email me or you can email Stu Foreman, okay? So I'm gonna go ahead and, oh, and we have one question or comment. Oh, do I have a typo? Public night is on the 7th? Okay. Okay, we will verify the public astronomy night.
Saturday, June 7th.
Yeah, we're just verifying. It is? Okay. Okay. Yeah. I could have typoed it. Okay, so we're going to get right to our What's Up presentation. Please welcome John.
Okay, thank you. It's my pleasure to be here. Now we see if this marvelous machine will work straight away. Almost. Okay. Okay, great. We're getting there.
You are going to have to join the Zoom meeting or they won't be able to see it.
Oh.
Yeah.
Okay. So let me. Just hold on a second.
We're just having a video lagginess. We're trying a new screen share, so give us 2 minutes.
Well, at least you can't watch me go through this. There you go. Okay, here it comes. Share.
Stop sharing.
Okay. All right, can you see it online?
I can see it
Yeah.
online, yes.
Right. Just a little bit about myself, because it's relevant to what I want to talk to you about. But I spent many years, over 35 years, as an accelerator physicist. And the most recent 30 years at Berkeley Lab. I retired. I still work a little bit as a consultant, but I work mostly on particle accelerators and some project management. So I was involved in some astronomy projects as a project manager. I'm not a professional astronomer, but I'm very interested in it. My current activities in astronomy are related to what Tara was talking about earlier, mostly outreach. So I love to go to schools and community events, take my telescopes, and show people the night sky and the day sky with H-alpha filters. So an outline of my talk is that I'd like to share with you part of my interest now in cosmology. And there are two key questions in astronomy and astrophysics, cosmology. And that's what is dark energy and what is dark matter. And the context here is with thinking about the Big Bang model. And I'll talk about the evidence for expansion, acceleration, and for dark matter. And in particular, I want to talk to you about technologies and new results from two recent instruments that were developed at Berkeley Lab that I had some connection to as a project manager. Okay, so the Big Bang model, I think we're all probably very familiar with, but at the beginning of the universe, almost 14 billion years ago, there was a very, very tiny, super dense, super hot volume of energy, and that rapidly expanded. That's the inflation period you see here. It grew enormously. It grew faster than the speed of light. So space-time can move faster than the speed of light, but the speed of light between objects within space-time cannot. But that's a very important point. It grew incredibly quickly, and then at the end of inflation, the plasma condensed into atomic matter, and that allowed the radiation to move freely through the universe. So that's the cosmic microwave background here. After that, there were what we call the dark ages, because this was before stars had formed. So there was helium and hydrogen and helium, a few little bit of other elements, very little. But that the light that was formed as the plasma neutralized spread through the universe, and it's the conglomerations of matter that are seen in the pattern of the microwave background here that seeded the evolution of the universe that we see today. So eventually stars formed. There's this anisotropy in the microwave background that shows where there were just very, very tiny overdensities and underdensities. But that led to the formation of giant gas nebulae, formation of clouds, and then eventually the formation of galaxies. And the universe continues to expand. So this picture shows space expanding. It's just a pictorial, right? It's not meant to look like this, but it's meant to show the rapid expansion of the universe over time. And of course, all this development of the universe over those years led to some detailed structure. So when we look out, we don't see anything uniform on the sky. Very little that's uniform on the sky, except light pollution. But we're trying to understand how this happened, right? Because if everything was uniform at the beginning of the Big Bang, then we would not see all the structure that we see now, and it arose from these quantum fluctuations. So together with the Big Bang, the most popular and successful description of the evolution of the universe has been the lambda CDM model. So we've heard about this in talks at this event several times. I just repeat what we've heard before, but lambda is the dark energy. So lambda is the cosmological constant in Einstein's general relativity solutions to the Big Bang. And CDM is cold dark matter. So it's dark matter because we cannot detect it electromagnetically, but we can sense its existence through gravitational effects. And it's called cold because it moves slowly with respect to the speed of light. And it does form clumps and halos around galaxy structures. So observations over many decades, and we'll see, so I got data going back over 100 years, but this has established that the universe is about 70% of its total mass energy. Remember, that's what Einstein concluded from his general relativity, that mass and energy are equivalent, E equals mc squared. 70% of the total mass energy in the universe is dark energy. About 25% is dark matter, and only 5% is normal atomic matter. So it's kind of makes me feel small because we don't know what on earth is going on. We don't know what in the universe is going on. So this little pie chart just shows that distribution. And what we think of as normal atomic matter, we call baryonic matter, and that includes protons and neutrons primarily. So what's the evidence for expansion of the universe? I think people have seen graphs like this before. So this is going back 100 years initially. Down the lower left here is the area that Edwin Hubble developed 100 years ago. In 1928, he published his first data on this that showed the Andromeda galaxy and other galaxies were far away from the Milky Way, and also that the galaxies were all moving faster the further away they are. So the key takeaway from this actually is that if you were a galaxy anywhere on this list, you'd measure the same distribution of galaxies from anywhere in the universe. So there's no center to the expansion, but all galaxies, all distant galaxies are moving away from each other. The whole universe is expanding. So what's the evidence for dark energy? And this came from another extension of that Hubble constant measurement. We're looking, in this case, for magnitude of supernovas, supernova type 1a in the far distant universe. So this is going up to a redshift of about 1 in this plot. So this is roughly 20 times further than that previous plot that showed the Hubble constant. So the data here, you can see where it's all clumped, but it runs along this light blue line. And the importance of that, while it may look kind of trivial, it's another straight line. But this was a huge surprise because it was expected that the universe would be slowing down due to gravitational effects, or the matter in the universe will be pulling itself back towards a point source. But the measurements that were made in the late 80s, 2 separate teams did very similar measurements, but they approached it in different ways, so systematics were taken out. And they agreed that this data is best fit by an increase in the expansion rate of the universe. So the universe is accelerating. Oops. So it looks pretty trivial, but Saul Perlmutter from Berkeley and Cal won a Nobel Prize together with Adam Rees in 2011 for this work. So that's the data. What is the evidence for dark matter? Well, dark matter is evident, as I mentioned earlier, from its gravitational effects. And so the first measurements that pointed out dark matter were done by Fritz Zwicky in, I think it was the 1930s. But a lot of data has been taken since then, including measurements. Fritz did it on the Coma galaxy cluster. So he's looking at distribution of galaxies themselves. But here's an example of measurements in radial distance from the center of a galaxy. So we're looking first in yellow here, observations of the velocity of stars as we go further out from the center of the galaxy. And then the stars thin out, right? So you got the dense core here. This is just pictorial, the galaxy in the background. But then as you go out, you get fewer and fewer stars. So you expect that the mass that's guiding the velocity of objects further away from the core of the galaxy, you'd expect that that mass would taper off. It would become, it reaches a maximum. And so the velocity of objects further away would decrease. But what we actually measure is that they continue to increase, even far away from the galaxy core, and even way far away where there's almost no stars, but there is hydrogen gas. And you can detect hydrogen from the 21 centimeter radio telescope measurements. So this is explained by the existence of something that we call dark matter. And the dark matter is in a halo around the galaxy and around galaxy clusters that adds to the mass, and that then gives this velocity distribution of objects that are orbiting the center. So what might dark matter be? We know it's only from gravitational effects, does not interact with the electromagnetic force. We can see its impact in the cosmic microwave background and the abundance of hydrogen and helium that were formed in the Big Bang. But maybe it interacts with a weak nuclear force, so it doesn't interact with the strong or electromagnetic forces. Maybe it will interact with a weak force. So there have been a number of proposals for particles that make up dark matter. And the 5 here, WIMPs, I'll talk about, axions, sterile neutrinos, glutathione particles, which are show up in theories like string theory, and even primordial black holes. But I'm not going to talk about those. I'll conveniently wipe over them and talk about WIMPs. Because WIMPs are weakly interacting massive particles. They interact through the weak nuclear force, but not electromagnetically and not with the strong force. And so I'll say a little bit more about that later. What might dark energy be? We see that the expansion rate of the universe is increasing. We don't know why exactly, but there are a number of potential causes for this. I'm going to talk about vacuum energy. There are other proposed causes, modified gravity, brane cosmology, and quintessence, but I'm going to stay with the lambda CDM model. So DAISY is one of the tools that is investigating dark energy. And DESI stands for the Dark Energy Spectroscopy Instrument. This is a new instrument on the telescope, the Male telescope at Kitt Peak, just outside Tucson, Arizona. So here's the Male telescope. Hopefully everyone can see the cursor bouncing around. And the DAISY instrument is primarily this black cylinder at the top here. So light comes in, it reflects off the primary mirror at the base of the strut structure, and then that comes back into optics in this black cylinder. The focal plane is at the top here. So DAISY is creating a 3D map of galaxies. And the purpose of this is to get a very detailed map of tens of millions of galaxies so that you can understand the structure of the distribution of the galaxies in the web of galaxies that we can see out as we look further out into space. So this shows a slice through the map that's being created. And you're looking from at the beginning of this circular distribution here is the Earth. So you're looking radially out from the Earth. There are a couple of wedges at the upper left and lower right. That's just where you're trying to avoid the Milky Way in the measurements, okay? So you can't see in that plane. So you're getting these two fans. And this is going out to redshift of about 4. So this is 12, 13 billion light years away. And the different color bands here are just different techniques that are used to identify and quantify the galaxies. And the inset here is this tiny little bit of the total map, but it shows the structure. And it's this structure that's most interesting. This is called, whoops. I know, maybe see better there, sorry about that. They're looking for what's called baryon acoustic oscillations. So in the very early period of the universe, the density fluctuations caused by quantum fluctuations, and then as matter formed, it would form denser and less dense clumps. And that the interaction between the more and less dense areas traveled at the speed of sound, right? So it's a pressure variation that's moving through the universe. Remember, the universe was so dense that the speed of sound at that time was close to the speed of light. So it's very, very fast, but it's an acoustic oscillation because it's a pressure density variation over time. So we're looking at the variation of that structure as you look further back in distance and further back in time. So the telescope itself, this is a very busy schematic, but what I'd like you to take away from this is that the telescope doesn't create images. They're not visual images, but what it does at the focal plane here, the light comes in from a distant galaxy, reflects from the primary mirror through this optics. It's got a very large 3.5-degree field of view, flat focal plane. And on the focal plane are fiber optics. They're carefully positioned, and each one of them is looking at a galaxy. So it's taking the light from that galaxy and sending it down to an array of very sensitive spectrometers. So this is a view of that focal plane. It's about 1 meter in diameter. And in that plane, I mentioned that there are fiber optics. Okay, so this is that plane again. And there are 10 petals. You can see one of these wedge petals here. But as you zoom in here, you'll see this little spot is, for example, one of the fiber optics. It's 100 microns in diameter, so it's a tiny little point. And it's positioned on the end of these robotic movers so that it lines up with a galaxy. There've already been many surveys of galaxies in terms of their position. So we know where to place the fibers to line up with the galaxy in the field of view. And then we can take the spectra of all these galaxies. So the key thing in this technology is that it is fully robotic, it's programmable, and it's very quick. You used to do these kind of experiments with kind of handmade or CNC-made plates. And you drill holes in the plates, and you'd have to take a plate off and put it back for a different exposure. This is orders of magnitude faster, so we can build up this map with millions of spectra and get a better understanding of how the structure in the universe evolved. So this cartoon shows zooming in onto that focal plane. You can see these are the robots that control the fiber optics. The fiber optics are in white, so you can see the signal going down from these. And as they all move around, positioning themselves for particular galaxies, signal goes off to the spectrometer, you get a spectrum of that galaxy. So this is, I should say that this is a data release from 2 months ago. So that's what's particularly interesting. They're not finished, but this shows the current map of at least the brightest galaxies that they've been looking at. And you can see the structure that goes back. It's in fairly clear detail here of webs and conglomerations of galaxies. But every point here is an individual galaxy. And the extent, the radial extent of that display was about, it's about 12 or 13 billion light years. So that's at the edge of the visible universe. So the latest data release, it's not conclusive, and the experiment will run for at least another year, but it does suggest that when the DESI measurements are paired with other measurements, that the effect of dark energy may be changing over time. So this is important because we're talking about lambda as the cosmological constant. If it's not constant, that could be new physics. So this is not expected, and it could lead to a deeper understanding and development of the standard model of cosmology. Should I keep going, Tara? I'm running slow. I got a few more slides, but all right. Okay, so LZ is very different, and LZ is looking for dark matter particles, not dark energy and the impact of dark energy. LZ is a detector. This is the core of the detector is this time projection chamber shown here. That's located about a mile underground in an old silver mine in South Dakota. It's underground just to shield it from all the electrons and crud that will just give you a lot of false measurements in the detector. So this is the core of the detector. It's surrounded by other detectors that allow to identify things that you're not looking for, and so you can veto those signals and ignore them. This is the time projection chamber. You can see a standard size human on the left here, so you get a sense of the scale. On the top and the bottom, you can see the photomultipliers that are sticking up out of the time projection chamber here. And inside this cylinder is 7 tons of ultra pure liquid xenon. That's important. It's got to be really pure so you get no fake signals from contaminants, and that there's a good chance that a WIMP might interact with the xenon nucleus. And here's a photograph of the photomultiplier arrays that go top and bottom of that chamber. So you see there's about, I think there's 170 on each side. Okay, so the idea is that if dark matter really is WIMPs, and they do interact through the weak force, then they could interact with a xenon nucleus that gives a characteristic signal in this detector. So 2 flashes of light. The first one, when the WIMP hits the nucleus, you get some scintillation, so you get a burst of light, this gold-colored photons here. You also get electrons produced. And so the electrons are displaced by the electric field around the detector, and when the electrons leave the xenon, they produce electroluminescence, and you get a second burst of light. So what the detector is doing is looking for those two signals separated in time and amplitude and shape, and they're looking for the particular characteristics of those 2 signals that would be expected from a WIMP. No WIMP so far, okay? But that's very important in physics, right? A null result is very important. It constrains the theories and the types of particles that might make up dark matter. So that LZ continues to operate. Other experiments are also searching for other types of potential dark matter particles. Okay, so closing comments. 95% of the mass energy of the universe is not well understood, so this is still pretty amazing, and we think we're very smart, and we are, but we don't know very much about the universe. Detecting dark energy and dark matter would certainly be Nobel Prize activities, so a lot of people are trying to do this. Some early indications that dark energy may be changing over time, but no sign of dark matter yet. But I think we're in a fantastic era of cosmology and astronomy, because there are so many wonderful instruments both in recent years, going back, 20 years or so, and looking to the future, space probes, satellites, gravitational waves. When I was in college, on Earth were they? So this is a terrific time. So I'm going to end there and just leave this list of my resources and image sources. Okay, thank you.
John, thank you. That was amazing. You're a professional, and it shows. Really enjoyed that. Okay, we're just going to take a quick 5-7 minute break, and then we'll get back at it. Thanks, guys.
Mountain View, but for the past few years, I have been working from my home here in Minnesota. So they are pleased to have me be remote, and I use telescopes that are all drive-by-wire anyway, so lucky me. All right. This is a plot of the solar system out to the orbit of Jupiter as of this morning. You will see the sun in the middle, and I'm doing this for the elementary school students. I would quiz them on which planets are which, but you already know that. Mercury is just behind the sun right now, conjunction. Jupiter's over on the other side too. And we've got the main asteroid belt between Mars and Jupiter, the Trojan clouds in front of and behind Jupiter, and then you can see the threefold pattern here for the Hilda asteroids in that 3-to-1 resonance with Jupiter. And we also have the near-Earth objects, which are defined as things that come within 50 million kilometers, 30 million miles of the Earth's orbit at some point in their own orbits around the sun. There isn't actually a ring right at 1 AU here. That's just an observational effect because we are, of course, on the Earth, most of the telescopes we're using, and thus it's easier to find things when they come very close. And so there's a bias to find things that are right at 1 AU, but there's really a smooth trend coming in from Mars and into the inner solar system. So the near-Earth objects are coming from the main asteroid belt. They're replaced every few million years. The main asteroid belt, of course, formed because Jupiter scattered the orbits of everything near it. So when asteroids collide, they erode rather than accreting. And we thus have a way of studying early history of planet formation from stuff that never accumulated up to give planets. Now, obviously, the dots on the picture are millions of times bigger than the asteroids are. You wouldn't be able to see them. If we zoom way in, of course, you have the largest asteroids, which geologists call the smallest terrestrial planets. So we have this new term of dwarf planets. It's not new anymore, but term of dwarf planets for things like Ceres and Vesta, where gravity crunches them down to be round. Ceres, size of Texas, 900 kilometers wide. It's got a core. It's got water moving around under the surface. It's got carbon compounds and salt getting deposited out when the water comes to the surface and evaporates. This, again, similar to more like the moon or Mars even than to the smaller asteroids. Vesta is a tricky one. It may just be reaccumulated debris of a previous collision. It's not clear how much of a core it has left. It's certainly lost large chunks of its volume, and it's heavily processed volcanic rock. So we have the Vesta family of asteroids that show up quite distinctly relative to the other asteroids because they've been through that higher temperature, higher pressure metamorphism. I mostly focus on the smaller asteroids, although some of the small vestoids sneak in. So that's what the objects over on the right are. We'll zoom in again. So this is a collage of asteroids and comets that have been visited by spacecraft. It's out of date now, but it illustrates the basic patterns. We have larger main belt asteroids like Letitia. It's 130 kilometers, 80 miles long. It is no longer round. So we have this dividing line, dwarf planets, and smaller things just stop being round because the rocks can handle the internal pressure. Gravity is 1% of what we're feeling, and it can handle being this very ovally blobby thing. But it's also lost large chunks of its volume to impact events in the main asteroid belt over the last 4.5 billion years. So something like Letitia is the age of the solar system, but it is not necessarily going to survive the rest of the age of the solar system before it gets a disruptive collision. And things much smaller than Letitia, like everything else you see there, are remnants of previous asteroid-asteroid collisions, except for the comets down at the bottom. I won't talk about those during my talk. If there's questions later, I'll try and answer them. But you see things like Matilda here, it's a pile of rubble, and it's also almost gotten broken apart again. So we've got multiple generations of asteroid bits running into each other, and it gets kind of confusing sometimes to figure out exactly what happened. But we do get very peculiar physical properties as a result. I'm going to zoom in now on this dot, the asteroid Itokawa. So this is the canonical example of that rubble pile structure. I explained to people that Itokawa is an interesting pile of rocks. So it's 540 meters, a third of a mile long. But you can see it's sorted out. There's individual blocks that are 80, 100 meters across, the size of the International Space Station. This one here, for example, in the middle. But then there's also little fine grained sand separated out very neatly. There's no air or water here, so what's doing the separating? We can talk about things like electrostatic charge, lifting up material and moving it around, which doesn't matter much on Earth, but when the gravity is 10,000 times less, you can move fairly big clumps that way with charge getting deposited sort of randomly by the solar wind. We can talk about thermal expansion and contraction, producing stresses and making stuff get forced off on a daily basis. We can talk about impactors coming in and shaking up the whole asteroid. Cratering doesn't really act the same way on a really small thing like this as it does on a larger object like the Earth or the Moon. And we can also talk about effects of radiation pressure. So back in the middle of the 1900s, a Belarusian engineer, Ivan Ostrovich Yarkovsky, worked out what we now call the Yarkovsky effect. He realized if you have an object that's out in space, it's getting direct radiation pressure from the sunlight coming in, but it's absorbing some of that sunlight and re-emitting it in infrared, and it's coming off to one side. And the direction it comes off depends on how the object rotates and its shape and its mass. So this is the Yarkovsky effect, and it moves asteroids' orbits around. We now also understand the Yarkovsky-O'Keefe-Radziecki-Paddock effect, which we'll call YORP. Worked out by a number of astronomers, that's all the names in there. Steve Paddock is one of the really first people to demonstrate this experimentally. You've got an irregular shape, you heat it up, the re-emission coming off is going to be offset from the asteroid's center of mass to some extent. And that will spin things up or spin it down depending on the direction of the torque. So over hundreds of thousands of years, something like Itokawa can, in the Earth orbits, it can spin up and break apart. And you have a different shape and a different set of torques, and then it can slowly recombine again. And that gives us a sort of contact binary shape we see here. And it also gives a way to completely reconfigure the entire surface. So we have another motivation for studying the asteroids, the history of the solar system. We also have they're simply being really, really strange as compared to Earth's geology. There is another reason we study the near-Earth asteroids in particular. I talked about how the population of objects is replaced every few million years. Stuff comes in from the main asteroid belt, mostly Jupiter scattering things, also Yarkovsky radiation pressure drift. But where are the asteroids going? Sometimes their orbits become so eccentric they fall into the sun. Phaethon is doing that now. It's very eccentric orbit. It's not actually hitting the sun, but it's slowly evaporating off and giving the Gemini meteor shower. Sometimes asteroids get scattered by Jupiter again and go out of the inner solar system. Sometimes they break apart from rotational bursting, this Yorp effect gone to an upper limit. And sometimes they hit something. Sometimes that's the Earth. So here's an example of a few different small asteroids that impacted the Earth. The three on the left were all found shortly before impact, so they have these telephone number provisional designations of when they were discovered. So 2002, 2023, 2024. We haven't had one yet this year, which is unusual. These sort of things happen somewhere in the world every few months, and typically about one of them per year has been discovered in advance. Normally, these things are the size of a desk. They don't cause any problems on the ground. They burn up in the upper atmosphere. And Peter Yuniskins, who works also at the SETI Institute, will run over to wherever in the world the meteorites may have fallen and try to pick them up. He did not go after this one here in Niagara in Ontario, because that was right along the edge of the lake. And nobody wanted to go scuba diving in the Great Lakes in November. So there's no meteorites from that one. So those are harmless, and they happen pretty often. And you can get meteor cameras and help try to chart the meteor showers and predict some of them. But larger asteroids, they're less common, but they can cause trouble. So on the right there's the city of Chelyabinsk in Russia. About 1 million people live there, southern end of the Ural Mountains. For anybody who hasn't seen the videos of what happened there on February 15th of 2013, I recommend YouTube, because there's lots of people with security cameras, dashboard cameras in their cars, and just around local sunrise, so 3:20 UT, a few hours later there, people are getting up, go to school, go to work. Suddenly there's a bright flash of light in the sky. It's an asteroid the size of my house, 15 or 20 meters wide, that came in at a pretty shallow angle. And all of the kinetic energy from its orbit and all the gravitational potential energy released as it fell down got converted to heat and light and sound in that fireball, which is about 10 kilometers above the city. Lots of people ducked, which was the appropriate choice. Other people just had no reaction at all, which would not have been my response. There's a video, somebody's driving, all he does is pull down the sun visor and keep going. That would not have been my reaction. But a bunch of people ran to the window to see the bright flash of light in the sky. The shock wave travels at the speed of sound. It reached the ground between 30 seconds and a couple of minutes later, depending upon where in the city people were standing. Nobody died, but it was a pretty near thing. There were about 1,500 injuries, mostly from broken glass. So we'd like to know about things like Chelyabinsk, at least long enough in advance to tell people to stay away from windows. If something like this happens out over the middle of the ocean where there's nobody around, it isn't a problem. Something like that happened way off of Cape Town in the Southern Ocean in the 1960s. Only was known about because there was early satellite monitoring for nuclear test spans stuff. They saw a flash, an optical flash, and no gamma rays. It's not a bomb. It's just an asteroid impact. But nobody was there, so it wasn't a problem. We'd like to know, again, most things like Chelyabinsk, in case they are over places where there are people. But what really motivated studying the asteroid impact hazard was this. So in the 1980s, Louis and Walter Alvarez, a father and son team working out of Cal, were trying to understand why everywhere in the world you go, there are dinosaur bones in rocks 66 million years old. And then in slightly younger rocks, there's no dinosaurs but birds, and there's a lot of other things missing. In the middle, there tends to be a clay and ash layer, and everywhere in the world in that layer, there's a bunch of iridium. Iridium is rare in the Earth because when you make a planet, everything heats up and melts, and the iron sinks to the middle and takes the iridium with it. The asteroids that didn't differentiate and melt still have iridium mixed into them. So the Alvarezes concluded somewhere in the world, a large ordinary chondrite asteroid impacted 66 million years ago. They didn't actually specify that particular type. They just knew it had to be something that hadn't been really thoroughly processed. We know that now because a team out of UCLA found a large chunk of it, intact meteorite from ejecta from the KPG impactor here out in the Pacific Ocean back in the 90s. But in the 80s, somebody was doing seismic studies in the Yucatan Peninsula in Mexico, and they noticed there's this big double ring circular structure buried underneath the current ground. And it's the impact crater from the dinosaur-killing asteroid 66 million years ago. It's roughly centered on the town of Chicxulub, hence the name. Again, if you're on the ground, you won't notice it unless you're looking for cenotes, these limestone fracture caves. Popular for cliff diving, cave diving apparently, but they form a nice big arc all around the edge of the crater. So this really motivated people to want to find as many asteroids as possible on Earth-crossing orbits and make sure they're not going to hit the Earth. This had been done by Glo Helene to some extent in the 1980s using big photographic plates down a Palomar, but things really took off in the 1990s when CCD cameras came in, and the sensitivity, of course, as you all know, is much better. And also you can program the computer to find the moving objects for you, so you aren't sitting there blinking plates back and forth all the time. There have been many upgrades since then. The two most active projects are the Catalina Sky Survey in Arizona and the Pan-STARRS project out in Hawaii. There have also been efforts to find things from space. The Chelyabinsk impactor I mentioned actually came from fairly near the sun on the sky. It was an eccentric orbit. It was on its way back out. So to find those, you have to go to space because if you're observing from the ground, you're, of course, dealing with sky and the sun being bright. The Wide Field Infrared Space Explorer WISE was originally designed as an astrophysics mission, but It turned out that looking at 90 degrees from the sun continuously with a cryogenic telescope in the infrared is really good for finding asteroids. And they found a bunch of near-Earth asteroids, sort of incidental to the original mission plan. But it was so successful that they got a mission extension specifically dedicated to that. And now there's a new spacecraft, NEO Surveyor, being built to do more spacecraft surveys going close to the sun to find that cone of things that are really hard to see from the ground. There's also the Vera Rubin Observatory in Chile, which is designed to go much fainter than the current surveys and also covers the southern hemisphere, which is currently not covered so well. So upgrades are ongoing. And right now, the current discovery rate is about 3,000 near-Earth asteroids per year. But almost all of those are relatively small because, again, there's more small asteroids than big ones. So this all got lumped together and called Space Guard after an old science fiction novel, Arthur C. Clarke, for those who remember it. The discovery rate you can see here goes way up starting in the mid to late 1990s when CCD cameras come in. As better telescopes and better instruments are deployed, discovery rate keeps going up. But the discovery rate peaked for asteroids a kilometer across and bigger on Earth-crossing orbits in 2000, and it has gone down to pretty much zero because we found everything on Earth-crossing orbits that bring them near the Earth at any point in time. There's a very small population of objects with orbital periods very slightly off from 1 year. And those spend 30 years at a time on the other side of the sun from the Earth. And we only see them when they just happen to loop around and phase up. So there's a couple we found recently, but we've addressed the impact hazard to the extent that we can say there will not be any impacts by objects bigger than a kilometer across in the next few hundred years. There is one asteroid, 1950 DA, which was found in 1950 and then lost until 2000. And then it was identified as having a possible Earth impact in 2880. I got to work on this a little bit when I was in grad school, but we still couldn't rule out the impact. It's been bothering me for 20 years now, which is terrifying. But also we have 855 years to make sure that's not going to hit, so I'm not too worried about it. But we do still have this possibility of regional problems from some unknown impactor. So we have survey programs now, again, trying to find as many things as possible. Some of you may have heard of a recent case for this, which is 2024 YR4, discovered in December of last year, hence the provisional designation there. Almost all asteroids will never get names because when you're coming up with many thousands of names every year would be really annoying. So this just means that it was discovered in the last 2 weeks of 2024, and it was somewhere around the 120th object picked up in that time period. It was initially found to measure its position, measure its velocity. We say it's on Earth crossing orbit, priority for follow-up. But then it became clear if we ran the orbit forwards 8 years, there is a possible Earth impact in 2032. And that's what you see here. Initial Earth impact probability, 1% or so. What does that mean? When the asteroid's on some orbit, we have some uncertainty in how fast it's moving in particular. We propagate the orbit forwards, the uncertainty region expands with time. In particular, it spreads out along the Earth's orbit, along the asteroid's orbit, which in this case intersects both the Earth's orbit and the plane of the moon's orbit, which this is unusual. That only happens 1 out of every few hundred or so, but it happened this time. So we have a line along which the asteroid could be, and that passes across the Earth at one point in 2032. This thing's only 60-ish meters across. It would cause regional damage, but we still want to know if it's going to hit or not. So this became a big priority for follow-up the first couple months of this year. And as more data comes in, we have a better measurement of the velocity. You'll see the uncertainty region shrink. As long as the Earth is inside that uncertainty region, the probability of impact goes up because the Earth stays the same size and the uncertainty region is getting smaller. But eventually, the uncertainty region will shrink so much that the Earth is outside of it, and then the probability of impact drops to 0. And that happened over the course of February of this year. See the uncertainty regions shrink as more follow-up observations came in. By the end of January, we rule out any possibility of an Earth impact. Sorry, in February, we rule out any possibility of an Earth impact. But the moon is still there. We haven't ruled out that possibility. So there's a 3-ish% chance that the moon will have a fairly significant impact in 2032. We can't rule that out yet. We need to get more data. There's some data being taken from the space telescopes in the next couple of days, actually, which may rule out the moon impact, or may have the probability go up a little bit more, and we'll have to rule it out when it comes back again in 4 years from now. We can observe it in 28, and then in 32, it hopefully will not impact, and then it'll just fly by at the distance of the moon, and everybody will be very excited. All right. Other times we have to have a bit more patience with the possible Earth impacts. I mentioned the case of 1950 DA. Other cases, you see an example here, 2011 AG5 was discovered in 2011. Possible impact chance 1 in 500. Again, there's just an uncertainty how little we know about the asteroid's velocity. Came back again 18 months later, so this is the patience part, can say that in 2040 it will be 3 times as far away as the moon, and again, the only people who need to be excited are astronomers, assuming I'm still working at that point. Hopefully. But I mentioned 2011 AG5 in particular because I was able to observe it as part of the asteroid radar team. So what we do here is not actually normal optical astronomy. Instead, we have high-power radio transmitters mounted on telescopes. This is the Goldstone 70-meter antenna in the Mojave. It's normally used for talking with spacecraft, but they let us use it for bouncing radar beams off of things. So the radar beam sends transmitter, secondary, primary mirror reflector back out into space, and we code it in time. So we measure the number of nanoseconds it takes the radar beam to go out, bounce off the target asteroid, come back to the Earth. And we can resolve the asteroid in line of sight distance that way, from the time of flight of the radar signal. We can also get Doppler shift of the signal, which measures the line of sight velocity of the asteroid. And then as the asteroid spins, we get relative blue shift and red shift, and we can make images like these. These are not normal pictures. Delayed Doppler images are their own peculiar thing, but they give us useful shape information. So I can tell you that 2011 AG5 is another one of those contact binaries, bowling pin, peanut, ginger root, whatever comparison you want to make. You also see a lot of things like this one up here, 1992 UY4 is the phone number, but the important thing here is all of these bright spots in the radar image, which are standing high above the surface around them, or they wouldn't be visible back here behind the edge of the echo. So that's a bunch of boulders and blocks scattered across the surface. It's another rubble pile. Almost every one that we can get good enough resolution to see boulders on is a pile of rubble. There's a couple of things that are actually apparently solid blocks, but not many. So this gives us more sense of the near-Earth asteroids as a population. We also see things like 2020 BX12 in the bottom there. This is one of the last asteroids observed by the Arecibo Observatory before it collapsed in 2020. And this is a binary asteroid. It has a little satellite around it. The orbital period in this case happens to be near to 2 days. So we observe it one day, it's in front. The secondary in front of the primary, the next day it's behind. And to fit the orbital period, we have the distance between the two components, and we have the size of the primary. We can get masses and density. That tells us these piles of rubble in some cases are less dense than water. So there's lots of empty space in between the blocks. That's useful information for understanding formation, asteroid collision physics. It's also important for discussions of asteroid deflection, and I'll get to that in a few minutes. All right. So this plot keeps getting more crowded, which is a great problem to have. Because the near-Earth asteroids are easy to get to, some of them require less fuel to get to than the moon, although the flight times are longer, and almost all of them are easier to get to and crucially back from than Mars. There have been a bunch of different asteroid missions by different space agencies. The first one was 25 years ago, near Shoemaker, landed on the asteroid Eros. For the Expanse fans, yes, Eros changed everything. I used that line at the science fiction convention. They were very excited about that. Anyway, the next one was the Itokawa mission, is Hayabusa by the Japanese Space Agency. This is the other side of the asteroid from before. They landed down on the asteroid, picked up a little dust, and brought it back to the Earth. Chang'e 2 went to the asteroid Toutatis as it passed by the Earth. So the Chang'es are the lunar mission series of the Chinese Space Agency. They had Chang'e 2 in lunar orbit. Toutatis happened to be flying by the Earth. They arranged to fly by the asteroid just at the time of closest approach. So the asteroid sort of runs over the spacecraft. This caused a little bit of confusion because I was observing Toutatis with radar at that time, so we had to make sure there wasn't going to be any problems with the high-power radio beam interfering with the radios on the spacecraft. Fortunately, there was no problem, and they flew about 1 kilometer from the surface. And I'm glad our radar measurements of how the asteroid was arranged in space from its rotation and where it was were precise enough, because I didn't want there to be a chance of a collision. The DART mission from NASA and ESA went to the asteroid Didymos and Dimorphos. I'll talk more about that in a few minutes. There are also a bunch of other asteroid missions currently in progress. Hayabusa 2 from JAXA and ESA is return samples from the asteroid Ryugu. The main spacecraft let go of the sample shell, moved off to the side, slingshot past Earth. It's going to fly by 2 other asteroids. The OSIRIS-REx spacecraft from NASA and the Canadian Space Agency went to the asteroid Bennu, brought back rocks from that, and is now on its way to the asteroid Apophis, which some of you may have heard of because it'll be passing very close to the Earth in 2029. It cannot hit the Earth, but it will get torqued around some and maybe get resurfaced, so OSIRIS-REx will see that happen. The Hera mission is a follow-on to DART that is by ESA and the NASA collaboration. Again, it also going to Didymos and Dimorphos. There is also now Tianwen 2, which is going to launch hopefully in about 16 hours, if I have the countdown right. The plan here is from the Chinese Space Agency to go to an asteroid called Kamo-Olalewa, which may be a piece of lunar ejecta. So look, the spectrum of the surface looks like it's part of the moon. What happened there is not clear. The moon, of course, gets hit by asteroids and they eject stuff, but how much goes out into Earth-crossing orbits, we don't know. So that'll be quite interesting to see. And they also plan sample return from this one, which is going to be very tricky because Kamo-Olalewa spins every half an hour. So it has to have a fair bit of tensile strength holding it together. It may not have any loose regolith to grab. And to land on it, without the spacecraft getting thrown into space, you'll have to come in right along the spin axis. So I'm not sure how well that's going to work. We'll see what happens. Destiny Plus is a JAXA proposal to go to the asteroid Phaethon. May also fly by Apophis on its way out if they launch in 2029. There's a bunch of other proposed asteroid missions. There's proposals for ESRO, from Indian Space Agency to do asteroid mission. There's one from South Korea. Those haven't so far been approved. The Chinese Space Agency has another asteroid mission. They want to demonstrate asteroid deflection using the same technique I'll talk about in a moment. But they may also go to the asteroid Apophis with a small satellite. And there's a couple other possibilities for Apophis missions too, because everybody wants to take advantage of it being easy to get to. The sample return missions here are all possible because the asteroids are easy to get back from. You don't have to come out of a deep gravity well to get back to the Earth. So we talk about Mars sample return now, but we've already had 3 asteroid sample return missions because it's that much easier. All right. DART. So DART's development as a result of a question. Say we find an asteroid that's going to impact the Earth. If it's small, like Chelyabinsk, we don't care. Everybody stays away from windows, hopefully. If it's very big, though, we might wish to talk about moving it to stop it from impacting the Earth. How can we do that? In the 1980s and 90s, people were focused on very large asteroids because they were worried about dinosaur killers. And there was lots of discussions out of Livermore of various ways of exploding asteroids with nuclear bombs. Fortunately, that is not necessary because we have no dinosaur killer that is happening anytime soon. Instead, we talk about other ways of deflecting smaller asteroids. One approach is kind of Star Trek. It's called the gravity tractor. You have an asteroid in space. You have the spacecraft out here. The gravity is very weak, but it's there. You angle the rocket exhaust so that it misses the asteroid and hover. Newton's third law, equal opposite reaction. The asteroid is getting pulled towards the spacecraft. We don't think of pulling a mountain towards us by standing next to it, but in free fall, this works. So you can very, very slowly move an asteroid off course. I was part of a mission proposal called ARM to try to demonstrate that, but it would have cost about $3 billion because you need a really heavy spacecraft, lots of mass to get lots of acceleration. So that was not approved. What was approved instead was DART, the Double Asteroid Redirection Test. This is demonstrating kinetic impactor asteroid deflection. Just run spacecraft into asteroid as fast as possible and shove it out of the way. The problem, of course, is the asteroid is big and the spacecraft is small. And the spacecraft doing the impacting is destroyed upon impact. So how do you measure the deflection? And this is where Andy Chang at the Applied Physics Lab at Johns Hopkins got very clever. He realized that if you take an asteroid, a binary system, like the one I showed you before, and run into the satellite, the spacecraft will be destroyed on impact, but the orbital period of the satellite will change around the primary. And the orbital velocities are very low, so you can measure a very small velocity change because it'll be a large fractional change in the period. And this was done. In 2022, September 26th, the DART spacecraft impacted Dimorphos, the satellite of the asteroid Didymos. There was a CubeSat from the Italian Space Agency that was tossed off to the side, observed the impact as it happened, but it couldn't stay to measure the orbit change, so that was done from the ground. And this is what it looked like. So DART had to steer itself going in because round trip light time was 73 seconds and can't steer from the Earth. So a lot of machine vision programming went into taking pictures from the camera mounted looking forwards, figure out which of the two asteroids is smaller and target to hit that object. And that was done. This is Dimorphos just before the impact. It was right in the middle. And big explosion of debris off to the sides seen by the CubeSat camera and then from the ground. The radar observations were able to see through all that cloud of dust because it's much smaller than the wavelength of the radar, most of the pieces. And we see the main bulk of Dimorphos. It's shoved along in its orbit by the expected amount, 3 times the momentum from the spacecraft itself, roughly, because all the ejecta coming off. And orbital period was changed by about half an hour. I detailed exactly what happened to the shape and structure of Dimorphos we don't know. The Hera spacecraft is on its way out now, having swung by Mars to save fuel. It'll be out there next year. And we'll see exactly what has happened here, but we have confidence we have at least one way to deflect an asteroid if we have to. There is a concern for smaller asteroids that they might shatter completely. The Chinese Space Agency is proposing to do 2 spacecraft kinetic impactor deflection where they have one spacecraft go out, match orbits with the asteroid, watch the other spacecraft come in fast. But if they use a target that's too small, they might completely disintegrate the thing. And you can't actually measure the velocity change so well. On the other hand, that would be one way of dealing with a small impactor. So we have ways of dealing with the impact hazard. It's the main point here, fortunately. All right, there have been a bunch of other asteroid missions to different places. To the main asteroid belt, there have been Dawn and Ceres. The Psyche mission is on its way out to the asteroid Psyche. The Lucy mission is going to the Jupiter Trojans, but it loops through the main asteroid belt every time. It goes between the Earth's orbit and Jupiter's orbit. It's phased up to go out to one Trojan cloud, come back past the Earth, go to the other Trojan cloud on the next orbit, and it'll pass through the asteroid belt several times over and flies by asteroids on the way. There's a dedicated asteroid explorer for the main asteroid belt being done out of the UAE now, Mohammed bin Rashid Explorer. I put some question marks here for MMX, the Martian Moons Explorer. Phobos and Deimos, of course, are the moons of Mars. Their surfaces look like captured asteroids, but exactly how they got into their current orbits from solar orbit is not clear. So hopefully actually have a successful Phobos mission and answer that question. I'm going to talk lastly about a few bits of results from the Lucy mission because they're a good comparison to the near-Earth asteroids. So these are small main belt asteroids, but you can see they look very similar to the different near-Earth objects. Dinkinesh here has that Yorp spinning top shape. So again, radiation pressure torques spin up the object. It bulges out around the middle. It sheds material. It'll keep spinning up. In this case, it looks like it actually shed material twice. So it would have been a triple system for a while. We've seen triple near-Earth asteroids, a couple of them. And in this case, the two satellites appear to have recombined very slowly, giving us this single contact binary moon called Salem. So same processes are acting in the main asteroid belt as in the near-Earth population. That shows up here too for this asteroid Donald Johansen, observed last month. It is very similar to the asteroid Toutatis. It's slightly different in size, doesn't spin quite as slow, but the shape is very, very similar. Another one of these elongated contact binaries. There's more craters here, so the surface is probably older, and it's in the main asteroid belt. The impact rate's a bit higher. So radiation pressure, of course, becomes less as you get further out from the sun, but the same processes are working in the main asteroid belt as in the near Earth population. So we can understand the one, we can help understand the other. All right, that is all I have in slides. Wanted to leave plenty of time for questions, and I will stop here. And thank you again.
Thank you, Dr. Busch. Okay, I'm gonna run.
Should I leave on the screen sharing if people want to see the pictures, or should I turn it off so I can see people better?
Go ahead and turn it off, I think. And then
All right, I'll bring them back up if people have questions about particular pictures.
All right. Start with some questions from the in-person audience.
Okay, was the white spot on Ceres, I remember that a long time ago, was that some type of salt?
Yes, that's so some amount of liquid water moving around below Ceres' surface. It dissolves salts out of the rocks. It comes up near the surface. It evaporates into space, leaves the salt behind. The best mixture I'm seeming to recall was some sodium hexahydrate mix. So it's not sodium chloride, halite. You wouldn't want to taste it. It'd be like eating rock salt off the road here in Minnesota in the winter.
Okay, is that a mixture of salts or is it?
Yes, just figured out exactly which mix would be impossible to tell without doing a sample return mission from Ceres. There's a plan for that, but it's not easy because it's big.
Oh, okay. Well, thank you. Very nice talk. Thank you.
Okay.
Is there any thought towards mining asteroids at this point, or is there any value in that idea?
So I have seen 3 separate generations of companies trying to do asteroid mining and fail because you can't actually make money doing this, which is quite disappointing to me back in grad school when I first realized this. People talk about mining asteroids for platinum. The nickel irons have some 10 parts per million platinum group metals in them, but extracting all of that and bringing it back to the Earth just doesn't make any sense at all. More reasonable plans for space resource utilization are things like sandbags for radiation shielding. So you take asteroid material, piles of rubble, you figure out some way of shoveling it into a bag. The problem is you're in microgravity, so how do you avoid the shovel throwing you up and you stand by the asteroid materials going down? It's not obvious how to bag stuff, but if you could do that reliably, you can make piles of sand and contain them and strap them around a habitat for human astronauts, for example. Other things people talk about have carbonaceous chondrite asteroids. They've got lots of water chemically bonded into the rock. If you heat them up to a few hundred C, the water boils off and you could condense it. And then maybe you could use that for doing rocket fuel or life support for humans, drinking water or oxygen to breathe. But there's a problem with that too, which is there's lots of other stuff in carbonaceous chondrites, stuff like mercury, arsenic. A colleague of mine, Alessandra Springman, did a project on this. They stuck a bunch of different meteorites into an oven at different temperatures and figured out what gassed out when. And you don't want to drink whatever you condensed off of asteroid material without some very careful processing first.
Okay.
Thank you for your talk. I have a couple of questions. One is, if all the asteroids were put together into one, let's say, planet, how big would it be? And number two, you talked about asteroids keep getting smaller. Are any asteroids getting bigger?
So as I talked about, the impact velocities in the asteroid belt are way, way higher than the escape speed of the asteroids concerned. Escape velocity from Ceres is less than 1 kilometer per second, not much less, but it's a little less than that. The impact velocities are a few kilometers per second. So the impacts erode, they don't accrete. That's why nothing built up in the main asteroid belt in the first place. The answer to the first question, Ceres is 1/3 of the mass of the asteroid belt all by itself, roughly. It's about 1,000 kilometers across, 900 some. So if you piled them all together, you're still getting something that's whatever the cube root of 3 is. It's not that big, much smaller than the moon. This was a problem for quite a while for models of planet formation. If we look at protoplanetary disks, initially they start off quite smooth. And you could say there's this much mass at this distance, and the terrestrial planets and the gas giant planets follow a fairly good line there. But the asteroid belt is way, way less in mass than it should be. There should be 20 or 30 times as much stuff. And asteroids running into each other only explain some of the depletion. But this we now understand to have been due to the gas giants moving around a bit in the early solar system, and that swept resonances back and forth and scattered away most of the initial mass of the asteroid belt. You hear about the late heavy bombardment on the Earth, that was due to that process. Lots and lots of asteroids coming in for the first few 100 million years until things settled down, and then there was far fewer asteroids than there were at the beginning.
Okay, I have a Zoom question. How did your career move you to asteroids?
Too much Carl Sagan at an early age. But more seriously, when I was in undergrad at the University of Minnesota, I was doing radio astronomy work with a professor named John Dickey. And he knew I was interested in planetary science stuff as well as the radio astronomy. So he told me there's this guy, Steve Ostro, in California, working on radar observations of asteroids. You should talk to him. And Steve offered me a job. So far, it's worked out.
Any more questions? Okay. Any further on the chat, or anybody want to unmute yourself online and ask a question? Okay, I think that's it. All right, thank you, Dr. Busch, for
Was
joining.
there somebody trying to unmute or not? I see people moving fingers to screens on Zoom. No? Okay.
No, okay.
One
All
other
right.
note, I have been showing off the 3D prints of various asteroids. Those are available on the Asteroid Group website if you want the 3D print files. Thank you all again.
Thank you, Dr. Busch. Appreciate it. All right, everybody, have a good night. We'll see you next month. See you up on the mountain.
If I can get here in June, I'm not sure. I don't see it on Zoom, I guess.